and Vincenzo of mechanical systems consisting of balls, masses, connected by springs. Sometimes the springs were very, very stiff, but nonetheless, that was the basic idea. So they had balls connected by springs, and they formed some kind of structure. And by engineering the structure of the various connections between the balls via different springs of different stiffnesses and different arrangements, they were able to kind of sort of bring out some behavior. Particularly, this behavior was usually manifest at the boundary. And to explain it and to capture it, you had to really worry about the sort of topology of this arrangement. So there was a topology which emerged from this sort of system. And we even saw some real realizations of this in the forms of Lego and laser cut pieces of plastic. What I want to show you today has a similar spirit. It's a mechanical system. I'm just going to show you a video now of what this mechanical system does. I couldn't bring it for you to play with. This is an experiment done in our lab. Okay. And in this mechanical system has the curious property that if you poke it on one end, it also has a funny behavior at the edge. Okay. And this behavior sort of stays confined to the edge, and poking it generates this wave that goes around in one direction only around this system. Okay. And before saying anything more, I should introduce the key players behind this video, which I'm showing you over here. Okay, first of all, Lisa Nash, who built this and did all the experiments and a lot of the calculations, which I'm going to tell you about. Alice Mary Reed and Dustin Kleckner. Alice Mary was an REU student. Dustin is a postdoc who's here in the audience. Vincenzo, who you know well. And last but by no means least is Ari Turner, who unfortunately couldn't make it here to join us, but was really a key player in helping us set this system up and understand it and get this whole project going. Okay, so what is it that I'm showing you in this video? What is it that you're looking at? What's the key ingredient that makes this different from the stuff that you heard about from Tom and Vincenzo? Well, the basic kind of key ingredient, the basic difference between this system and the other one is that we took what are, the masses, the balls in their system, and we replaced them with gyroscopes or spinning tops, if you like. So let me sort of sketch this. My sketching abilities are about to be tested. Okay, here's a spinning top. Okay, it's spinning around. Okay, and we connected these spinning tops. This is sort of a sketch. It's not quite like this via springs, and we're able to get this behavior out of it. Okay? So since this is really the fundamental difference and the basic ingredient which we're adding to this story, let me spend a little bit of time, just reminding us all how spinning tops work and how to think about them. Okay, and this is, however familiar this is often a confusing topic for all sorts of specialists. Okay. So I thought we really should kind of have a look at it. So what's funny about spinning tops? What's funny about spinning tops? Well, one of the things that I find very funny about spinning tops, this is a sort of model spinning top over here, okay, is that usually when you take an object and you sort of pivot it, like a mass connected to a point, a pivot, right? And I displace it, then it just shakes back and forth without rotating in that direction over there. Okay? And this is what a mass suspended by a piece of string or a spring would do. And you can see it doing it over here. But if we add an ingredient to this mass, if we add some angular momentum to this mass, that's the spinning part, then when we suspend it, instead of dropping, it exhibits a very different behavior. Right? It rotates around this axis over here. And so let's just remind ourselves why this is and how we think about this. That was dangerous. Okay. So, well, the key ingredient, what's the difference between our mass, our pendulum, and the gyroscope that we just saw? Well, the difference is that we've added to our system angular momentum. Okay? Okay, and the angular momentum, well, it's just the, let's say it's the sum of the radius of each particle inside our system from some axis crossed with the momentum of each particle inside our system. Okay? And what we're interested in is the rate of change of angular momentum, because we're interested in the dynamics of the system. So we're interested in d by dt of L. Okay. So, well, d by dt of L is just going to be the sum of dr by dt cross p plus r cross dp by dt. Okay. Now, but if we think about this particle by particle, these two are actually parallel to each other, right? Because p is just mv, p is m times dr by dt, so we cannot worry about this term over here, and we have our basic equation which describes the evolution of systems with angular momentum, which is that the rate of change of the angular momentum is given by the torque, which is the sum of r cross the forces acting on the system. This is just equal to the force acting on each particle. Okay. So now we can think about our gyroscope. Okay, so we had our gyroscope, it was suspended from here, had an axis like this, and it was rotating this way at a reasonably high rate of rotation, as high as I could get it. So the angular momentum is pointing this way. And the force acting on it, other than the pivot, which is just a constraint, is the force of gravity. And so the force of gravity pushes down on the center of mass of this object. And so what we're going to have is that the rate of change of the angular momentum is going to be equal to the torque, and the torque is mg times this distance over here. I'll call it little l. Okay, little l. And it is, so our force is mg, our arm is L, and we need to take our cross product, right? So the force is down, the arm is out, so the direction of this torque is out of the board. Okay? So if we imagine that this is an orbit, and we characterize this angle over here by phi, this is going to be in the phi hat direction. Okay? Now, you might have noticed as this thing turned around, it didn't really slow down, it didn't really change speed, so the magnitude of L kind of stayed fixed. And so in fact, this equation predicts what we just saw, right? Because what we just saw was that the evolution of the angular momentum, which was the axis of our spinning top, was out of the board to start with, right? And then it continued in this phi direction and generated a rotating motion like this. Okay. Everybody happy with that? I always find it a little discomforting. Okay. So, so what do we notice about this? So first of all, there's something kind of very counterintuitive about this evolution, and that is that you what's counterintuitive to me is that you push in one direction, and the system responds at 90 degrees to the direction that you push in. Right? And this is kind of very contrary to your usual kind of expectations from inertia, where you push in a particular direction, and a body continues in that particular direction. Okay? So, but nonetheless, it's physics. It's freshman physics, okay, and it works as you just saw over there. Okay. Everybody happy with this? See some nodding. Nobody's no discomfort with. Okay, good, excellent. So then I won't tell you about how to think about nutation. Let's see. So what I'd like to do now is consider, right, what the consequences of having objects which are spinning are for. We're going to start to set up our basic building blocks, like you do for normal elasticity, but our basic building blocks are going to be the gyroscope. So we're going to specialize. We're going to do some specialization, which is what Tom and Vincenzo did. We're going to consider a network of these objects, and we're going to displace them by small amounts, and we're going to derive the equation of motion for our spring network, just like Vincenzo and Tom derived their equation of motion for their mass and ball network. Okay, so we're going to consider our basic building block to be a gyroscope that's pivoted at a point, and it's spinning in a direction like this. It could it's going to have some sort of mass. This will be a disk, and it's spinning this way over here. And the variable that we're going to be interested in is the endpoint of the gyroscope. We're going to consider displacements of this endpoint of the gyroscope. So, and we're going to be considering small displacements. So really everything is going to be happening in this plane over here. Right? So this displacement when this gyroscope is tilted, okay, is going to look something like this. We're going to have a delta over here. Okay, and I'm going to call this delta. I'm going to parameterize this system in 2 dimensions using this combination over here. Okay. So the real part of my displacement, this is my sort of delta if you like, total delta, is going to be a displacement in the x direction. And the complex part is going to be a displacement in the y direction. Okay. So, well, let's think about this. So the angular momentum in this case is pointing mostly along this axis over here. Okay. So if I want to consider pushing on this axis over here, then as we saw, the correct way to think about what happens next is in terms of a torque. And this torque is generated by this force and this axis over here. Okay. So if I have a force, the torque is going to be given by the axis, which is mostly vertical. Okay? So it's mostly in the z direction. There's going to be a length over here. Okay? And it's going to be given by the cross product of the r, which is essentially along z, with the force. Okay? This is just our equation for the torque, written down as we wrote it before. Okay? So if we try to write this in the same kind of notation, then one way to think about this is that, well, if we just simply transcribe it, the torque is going to be, if we write the force as fx plus I fy, right, then the effect of taking the cross product with the z direction is to take the x component and make it into the y component, and to take the y component and make it into minus the x component. Okay? And the way in which we can achieve that is by saying that our complex torque, our torque is going to be going to map onto I times our force. Okay. Everybody happy? We've just simply okay, so z is the z-axis.
I'm sorry, no, I just mean I'm reading.
Oh, okay, sorry. I'm just saying that the response, right, the effect of taking the torque, what I'm trying to do is I'm trying to rewrite this equation over here. L dot is equal to the torque. Okay, so maybe I should start by doing that. So what is L dot, right? Well, L dot really only has variations by picking up components in the delta x and delta y direction. And the magnitude of L dot doesn't really change very much, because we're enforcing a constraint that this thing is spinning. So L dot, in fact, is psi dot times the magnitude of the angular momentum of the spinning top. And the response, the direction in which there's going to be a change in the angular momentum is going to be perpendicular to the direction in which we're going to be pushing with the force. Okay? So my equation becomes L psi dot is I L times F, where F is Fx plus I Fy, and psi is delta x dot plus I delta y dot. Yes, yes. I might be missing a factor here and there. What I'm trying to get over here is the basic ingredient which goes into our equations, which is this response of the system at 90 degrees to the direction you push in. Right? And when we do this in complex coordinates, right now F could be from anything, right? So F could be from me going in and pushing it, or F could be from gravity trying to restore the position of the gyroscope, or F could be from one gyroscope pushing on the other gyroscope. Right? It's a completely general F. No, that's a small L. This is the angular moment, the zeroth or the angular momentum of the spinning top, right? Because our equation is dl dt, right? Our vector L points mostly down, but can pick up components this way. So all the dynamics are by picking up these components over here, but still we have to multiply them by the L naught. No, because the rotation is in this direction over here, right? So r cross p points downwards, because r is from the center of the axis to the rim, right? And so the angular momentum, if I have a spinning top that's like this, right, then the velocities are all in the phi direction, the r's are all in this direction, so the angular momentum is in this direction. Happy? Everybody's so good. Okay. So
you just mean take real imaginary part to get the original?
Yes. We're considering small displacement, take real imaginary parts, and we'll get the displacement. Yeah. Okay. An interesting thing to sort of start seeding and just thinking about a little bit is what's the difference between this and the system that Vincenzo and Tom considered? Well, the difference is, I mean, we could have also used this complex notation to solve their system. We're not doing anything funny. It's first order in time. So what would have their equation of motion have been? M
Always make it first order.
Huh?
You always make it first order in time by having
Two equations.
Two equations first order in time.
Yes, but here we have one equation first order in time.
We have one equation second order.
Yes, and we have an I, and there's no I over there, which is intrinsic to the building block.
You can make Hamilton's equation for position and momentum.
Yes, absolutely, but then you have two equations.
Two equations, yeah, just like here.
Well, no, here's one equation for one system and one equation for another system.
More similar.
Well, we'll see. Okay, so since we're kind of familiarizing ourselves with writing a kind of elasticity and things in this way, I thought I'd just do a couple of examples, right? And so the two examples which I want to do is to take one of these gyroscopes, and we're just going to solve this equation of motion in the presence of just gravity, right, to see what we get. And then we'll see how we're doing for time. We could solve the same equation with the language of F equals ma and see that we get an oscillation like this. And then we're going to talk about interactions. So, well, our equation is I dt of psi is equal to, I think, plus or minus f. I think I have some ambiguity in my notes. We'll sort it out in a second. Okay. So I want to solve this equation, and I want to solve this equation for an initial condition where I have one of these gyroscopes displaced by some amount psi naught, okay, at time 0. Okay, so, well, it's a linear equation. Okay. The force, in this case over here, is going to be essentially a restoring force. Right? If we think about our object having mass, it's going to be a restoring force where the magnitude, the component of the force, which gives us the torque this way, is going to be proportional to the displacement. Basically, gravity for small displacements acts exactly like a spring. So the form for our force is going to be equal to minus k times the displacement. Okay? So we have a linear equation, and we're looking for oscillating solutions. Okay, so in general, our solution is going to be equal to psi, which has two components. I'm gonna call them like this. Okay. But really, these are equal to some amplitude times e to the I omega t plus some other coefficient, which I'm going to call like this, e to the minus I omega t. So in fact, if I substitute this guess for my solution into this equation, I really have two equations. One for frequencies which are positive and one for frequencies which are negative. And so I can then go and solve this equation. So I have the time derivative of psi is going to pull down an I omega. So I'm going to get I times I omega, right, times L e to the I omega t. And also I'm going to get an minus I times I omega times right star e to the minus I omega t. That's my derivative acting on these two terms. And then on the right, when I match the frequencies, I get minus k L e to the I omega t plus r star, minus k r star e to the minus I omega t. Okay. Did I miss anything here? No. Okay, good. So now we can just cancel off our frequencies, and we have our solution. And our solution is that we have minus omega is equal to minus k for the left-moving component. Right? So we can start writing our solution. Psi is equal to L e to the I k t. And then for this equation over here, I have a plus omega is equal to minus k. Right? So omega is equal to minus k for the right-moving component. So really, what I found is that both components, in fact, have the same time dependence. Okay? And so now I can just say, well, at time 0, psi is equal to psi naught. It's some displacement. So psi naught is equal to L plus r star. Okay? And so psi is equal to L plus, actually it's equal to psi naught, which is a displacement, times e to the I k t. And what this describes is simply a clockwise rotating wave. So we've taken a gyroscope, we put the restoring force, and we got exactly what we expected, which is something that rotates clockwise. I see mild discontent. Yes?
So is this L is the angular momentum in one direction and R is the angular momentum in the other direction? Or
For the moment, they're just coefficients, which I've written down in a suggestive notation. Right? But really what they are is exactly what you said. So you have a component of, when you're putting it into your equations, you have an amplitude for what you think is going to be left moving and an amplitude for what you think is going to be right moving. Now it can happen on you that in one particular case, there's only one component, if you like, and then that's only left. And so both coefficients merge. And this captures, what we saw with the wheel, but we could also take one of our single gyroscopes in the experiment and let gravity act on it and observe that the motion it executes is really an orbit like this. The orbit is only in one direction. Okay? And we can color it by the phase, right? And the amplitude is roughly constant, which comes from that. Am I out of boards? Oh, look. Okay. Everybody happy? We can go quicker. Okay. You can do the same thing, right, for a mass and a spring. Okay. And if you do this, what you'll find is that you need to worry about both your coefficients. So actually, without doing all the algebra, can you guess what's going to happen if our equation of motion is dt squared instead of I dt? We're still going to write down our solution like this. What are these coefficients going to come out to be? You're going to have an omega squared instead of omega, exactly. So the left-hand side of our equation is going to have an omega squared. It's going to have a minus omega squared is equal to, right? And on the right-hand side, we're not going to have this coincidence of only having one way motion. We're going to have an equal amount of right motion and an equal amount of left motion. What that translates to in terms of coefficients is that R is going to be equal to L, where star is the complex conjugate. In other words, the time dependence of masses and springs is going to be psi naught cos of kt. We lose our rotation. We have an equal amount of left and right. Okay, so then something just oscillates like this. Everybody happy? Okay, so let's connect them by springs. Okay, so let's write down a model for our force that connects the two gyroscopes. So we're going to say that our two gyroscopes are sitting at these two sites over here, right? And they're joined by a vector b, okay, which is just a complex number that takes us from here to here. And at each site, we have a displacement. We have site 1, we have displacement 1. We have site 2, we have displacement 2. So what's the force going to be between these two? It's going to be what? Exactly. So we're going to have an extension or a compression of the spring, right? And this, let me just make a decision here. How are we doing for time? Yes, okay. We're just going to have an extension or a compression of our spring. And so we have to calculate how much the spring is extended or compressed. Okay? So there's different ways that we could do this. Let me write a way that I find particularly simple, and then we can analyze the other ones. So we're considering infinitesimal displacements. Okay? So we're considering very, very small displacements. So if I take one of these displacements to be perpendicular to this spring, and this other one, for example, to be perpendicular to this spring, then what's the extension of the spring going to be? Zero, right?
Oh.
It's zero because if I take something like this and I displace it infinitesimally like this, right, the change in length goes with the cosine of the angle, right? And this cos of delta theta, and this is the first order, is 1 plus delta theta squared. Okay? So the only displacement that matters as far as compressing or stretching the string is the displacement which is along this direction over here. Okay? So how do we find that displacement? Well, a sort of easy algebraic way to find this displacement is to rotate our system of two springs. So if this is theta, which is the argument of b, okay, we can simply take we can take e to the minus I theta b, okay, and rotate our whole system over here, which basically means rotating our little difference vectors, which are psi 2 minus psi 1. Okay? And once we've rotated our system, then there's a very easy way of finding the component which is perpendicular and the component which is parallel. Okay? And the component which is going to be parallel to the line joining the two is just the real part of this expression over here. Okay? And this force, so this is going to give us a magnitude of our compression or our stretching, and this force is going to be in a direction which is given by the angle which joins the two. So we need to rotate it back, and we get e to the I theta b, and this now gives us the force that joins the two. So we can expand this out, right? And what we're going to find is psi 2 minus psi 1 plus e to the 2I theta b, right? Psi 2 bar minus psi 1 bar. That's just taking the real part of this, right? So it's psi 2 minus psi 1 plus the complex conjugate. This becomes a e to the plus I theta times psi 1 bar minus psi 2 bar. You multiply it by this, and you get this. There's a reason why we're doing this in excruciating detail. So this is our basic. Oh, I'm missing equation bar minus psi 1. Okay. And then there's also, of course, in front of this a factor of the spring constant over 2 to make this into real force. Okay. So this is going to be our equation for the force between two gyroscopes. Okay. So our full equation of motion for these two gyroscopes is going to be E I dt, I dt psi 1, right? There's going to be a force which pins it, right? So it's going to be, we'll call it omega pinning times psi 1. Plus there's going to be the effect of the second gyroscope on the first gyroscope. So this is going to be k over 2, psi 2 minus psi 1, plus e to the 2 I theta psi 2 bar minus psi 1 bar. Okay. And for the other gyroscope, we have the same equation with I dt psi 2 is equal to the same thing with 1 replaced by 2, and theta going to minus theta because we're now looking at the arrow from bond 1 to bond 2 instead of bond 2 to bond 1. Okay? So this becomes the equation of motion for a pair of coupled gyroscopes. Everybody happy? Good. Okay, so maybe we'll speed up a little bit. So this right-hand side over here is simply an expression of the force matrix. Right? So all we've done at this point is we've rewritten what Vincenzo wrote, right? For example, for the rotors on the chain, where you'll also remember there was a cos of 2 theta coming in. This cos of 2 theta is going to be important. And we've just written the force matrix for this. Right? And then when we solve it, we're always going to write the psi n, right? It's going to have two components, a psi left and the psi right. Okay? So these two equations are always going to become 4 equations, one for the left moving and one for the right moving. Okay? And the point which I want to make over here is that everything on the right-hand side of our resulting equation is exactly the same as what Vincenzo and what Tom had. Okay? So what's the difference going to be? Well, the difference comes from the left-hand side. The difference comes purely from the dynamics. Right? And the key difference is this I over here. And the consequence of this I over here is that when we try to solve the eigenvalue problem for this coupled system, right, we're going to make a substitution which is e to the I omega t, right, for psi naught. The dependence is always going to be e to the I omega t. And when we have a second order derivative, this is always minus omega squared. But when we have the first order derivatives, we're going to get a difference between the two equations for the left and the two equations for the right. And that difference is going to be a minus sign. So our eigenvalue equation is always going to look like, in one case, it's going to look like omega squared, psi 1 left, psi 2 left, psi 1 right, psi 2 right, is equal to some force matrix times our coefficients over here. So actually, I should just, to be consistent, I should call this left, left, right, right, 1, 2, 1, 2. Okay. But when we're considering our gyroscope equation of motion, we're going to get a minus sign. This is going to become an omega, and we're going to get a minus sign in front of this term and in front of this term. So when we go to solve for our eigenmodes and eigenvectors, we're doing the same thing that Vincenzo and Tom did, where we're going to be diagonalizing the dynamical matrix. But there's a difference in a dynamical matrix, which is that for the gyroscopes, the dynamic, if I pull these minus signs over to this side over here, it becomes the same equation. But in the case of Tom and Vincenzo, this dynamical matrix had these two blocks had the same sign. And in our case, it has a minus sign. So at the level of the dynamical matrix, you're really solving the same problem, right? But you're doing something which is dividing it into two parts and changing the sign of one of them. Okay? This has some significance, but I don't want to get into that now. Yes? Yes. Yes. Exactly. Yes, exactly. So in some sense, what Tom and Charlie and Vincenzo did was to take this dynamical matrix, which had plus on both sides, okay, and to split it into two different matrices, one which had the plus plus and one which had the plus minus. This is like the trick that Dirac did for example, to get two first-order equations from a second-order equation. Okay? But in our system, we directly have this as our dynamical matrix. Okay? So this is sort of formally how, going from just putting an ingredient of a gyroscope into the system translates into the elasticity of the system. Okay? And the key place in which it comes, if you've gone away and calculated systems which were elastic, and you have all your dynamical matrices, well, now all you have to do is put this minus sign over here, don't take the square root, and you'll have all the normal modes for a system of gyroscopes. Yep?
One other advantage we have, if you have structural weighting, you can have this property at the level of linear waves.
Yes.
You don't have to go to nonlinear.
You don't have to go to nonlinear waves. Yes. Everybody happy so far? Let's see. Okay, good. Okay, so that's all I'm going to do in terms of explicitly working out examples and calculating things. What I want to do now is go and look at systems where we're going to look at a lot of these things interacting, and we're going to see what phenomenology comes out. Right? And we're going to see some funny phenomenology, like I showed you in the first video, and then we're going to come back to this equation over here and try to see how this is making a big difference and how this is determining the funny behavior of our system. Okay. So let's see. So there's a little bit of technology. Oh, yes. I was going to show you, I didn't write this out in full. Okay, we didn't solve this in full, but you can do it. It's an exercise. Okay. What do you think the answer is going to be? What do you think the normal modes of the system are going to be? Uh-huh. Okay, so one is going to be this, right? And it's going to be two rotating like this where the spring doesn't change length. What's the other normal mode that you would expect? You expect a normal mode where there's there's a change of stretching and compressing, right? Just like for a regular spring, you expect this. Okay? So I can post this notebook for you guys if you like, but I kind of just did the algebra for what we just said. Okay, and indeed, if you solve for the two, if you just translate this, right, it's just a 4x4 matrix, and you find your eigenvalues and eigenvectors, and you plot them, then you find that you get this mode over here, where there's no change of spring. You get this mode over here, goes the same way, no change in the length of the spring, and there's no difference between those two modes. They're the same modes. Okay. And same thing over here. We get the counter-rotating mode, and same thing, over here, we get this antisymmetric mode. Okay? And really, the two modes are exactly the same as each other. If we did the same thing by taking the same problem and just substituting the bottom half of the matrix, the dynamical matrix being the negative of the other, we would recover the normal modes for the spring and ball system. Notice this one is moving to the right. This one is moving to the left, because now we have both possibilities for springs and balls. And this one is just oscillating back and forth. And this is the antisymmetric one, which is the one you'd expect for the normal modes of two matrices. Yep?
Tell me how to think about having two equivalent modes. Like you said, instead of having a clockwise and a counterclockwise, you have two.
You have two clockwise. It's the same calculation that we did over here, right? And we started off, it's a little bit how we've decided to divide the system up. It gives you a bit of a degeneracy. We decided to divide the system up into left moving and right moving. And then when we solved this particular case, we found that the frequency for the right moving was minus the frequency for the left moving. And that enforced that everything was right moving. So that's the translation into your eigenmode spectrum, that you're always going to have double the number of modes, which are the same, positive frequency and minus frequency, which is not the case for the other system. And so then we can take two gyroscopes from an experiment. We can let them interact with a spring that I'm not showing you. We can track them. Right? And what we find is indeed there are two frequencies, right, that characterize their motion. And if you select one frequency and figure out the orbits of these two, right, then we have an orbit where they're in phase, the same color, and they're always rotating together. And we have an orbit where they're in antiphase and they're oscillating with each other. So they're behaving exactly as you might expect. So what I want to do now is consider instead of 2, we're going to consider a whole bunch of them. Okay? And so we're going to consider a particular lattice. We're going to start with one lattice, and the lattice that we're going to start with is the honeycomb lattice. And we're going to ask the question, well, what does the spectrum of the eigenmodes look like for this lattice? And here is the spectrum for masses connected by springs. Okay? And here's the spectrum for gyroscopes connected by springs. Okay? Huh? We could do other lattices too, but we're starting with the honeycomb. Yeah, it's a long story why, but it's not actually fundamental that it's the honeycomb. What I'm telling you is not peculiar to the honeycomb lattice. Okay. It's not peculiar to every lattice. There's only some lattices it works for that we found so far, but honeycomb is one of them.
And is there any common properties of these?
We're working on that. Okay. So we can ask, what do the eigenmodes look like? Right? Before we had our two ellipses, right, for characterizing the eigenmodes of two of these gyroscopes. So we're drawing all our eigenmodes by showing their orbits. Okay. And we can scan through the different frequencies, right? And all the modes look very similar in some sense to the modes that you'd expect in an elastic solid, right? There's waves inside the bulk. There was a sort of jump over here. There was a slight change. The character's changing a little bit, but they're all sort of sitting there in the bulk. This is for periodic boundary conditions. Okay? So we can take a couple of these images, which we're flashing past very quickly, and look at them more carefully. And what we see is that what we have is sort of, naturally what we would have expected also in a spring and ball system. We have a lower band over here, which is an acoustic band. It's very hard to see over here, but an acoustic band, elements in a unit cell move together, and elements, so we see that over here. It's a little hard to see. It's easier to see over here. Neighboring gyroscopes are sort of moving together. Yep.
So this is the internal angular momentum and being transferred, all the L.
The L is fixed.
It's fixed.
It's fixed by a motor that just keeps it at that.
Or angular momentum from the recession, right?
Yes, it can flow the angular momentum of modes in some sense, exactly. Yes. There's probably some good way to think about it in terms of spin orbit, but yeah. So, yes, in all these things, our masses are connected by springs, and they're also pinned. Okay, but none of what I'm showing you over here depends on the fact that they're pinned. We could take that pinning, go to 0, and everything would look the same as far as this is concerned, except that, of course, the pinning is going to shift the lowest frequency in the problem up to the frequency of the pinning. But the fact that we have two bands like this comes from the fact that we have two atoms in our unit cell, and that's what gives us the two pinning, the two bands. Okay? So we have a lower band, which is an acoustic band, and we have the upper band where neighboring gyroscopes move in antiphase, right? And so far, it's pretty much similar phenomenology, yes?
Why is the number of states different?
It looks like that, but it isn't actually like that. You mean in this system and this system? Oh, I think we did different.
Just different system sizes?
Yeah. So first, let me verify that they actually are different numbers. It could just be the question of the degeneracy. But in this case, we picked only the plus, because in this system, you always have plus frequency and negative frequency. So sometimes we pick only the positive frequencies. And so there's, in fact, a sister kind of negative frequency version of this that carries no information. And that would give you roughly double the number of modes of this, which would match with that. And so the keen eye. OK. And of course, we've kind of done this in terms of normal modes and solving explicitly for a periodic system, but we could have also gone to Fourier space, right? And there our description is that we have two bands, okay? And we have a upper band, which is our optical band, a lower band, which is our acoustic band. And what we see this is now our kind of full band theory. So we can consider waves in both x and y direction. So we pick up an extra dimension. And what you see over here is that the fact that we had, in this case over here, this gap that separates the two is reflected in the fact that the two bands don't touch. And the fact that, in this case over here, the two bands seem to touch each other is because, in fact, the mechanical properties of this structure over here, where we don't have gyroscopes, are sort of quite famous. They're the ones of graphene. And we have these kind of Dirac points, which were sort of reflected in the fact that these two bands touch over here. So that's one difference between these two systems which is emerging. But the interesting thing that happens is when you now go from having an infinitely big system or a periodic system and you make it into a finite system. So when we make that step over there, we can do the same normal mode decomposition. And what we find is that there's sort of no real difference to this system over here, at least in the appearance of the structure of the modes. But if we look at the system of gyroscopes, we have something funny happen. Where before we had a gap with no states in between the two, we have a bunch of states that have appeared. And so now we can go and look, and we can ask, well, what do these look like? So we can go through our whole spectrum, and the bottom looks like just the same as it did before. And we go through this region, and you'll have noticed there's a kind of emptying of any motion inside here, and then the top looks as it looks before. And if we just kind of zoom into this region over here, what you see is that all the modes which are sitting inside this gap are localized to the edge. Another thing which is kind of maybe not easy to see from this, but you could also infer from this, is that if you look at the phase of these modes, the phase of these modes is one directional. If you look at the gradient of the phase between two neighboring things, it's going in one direction only. And that's granted a little bit hard to see in this. So what we can do is we can take one of these systems, now go to the time domain, and excite it a little bit, make a little wave packet of these edge modes. And what we see when we do that is that indeed these edge modes are chiral. And they propagate around only in one direction. So what's responsible for this? Angular momentum, so precession. Okay, so we have, that's a good point. So we have gravity in the problem, right? We have gravity which is pushing down, and gravity is causing everything to move, say, clockwise. So what's the big surprise that the modes move clockwise? Right? Maybe it's as simple as that. So let's try, right? Let's just take the same system, and let's suppress these terms over here. Let's kill gravity. Let's kill the restoring force, and do the same thing. We're going to diagonalize, and we're going to look at the normal modes. We don't need to do all that. We're just going to jump straight to exciting it and seeing what happens. Here we have a system where gravity is 0. So there's no bias coming from gravity. And we have the same behavior. Okay. Yes? Okay. You probably know the answer, but we're building to it. Okay. So it's not just gravity. Yes?
How exactly do we excite the system?
Oh, good question. So we excite over here. We take one of these and we wobble it. And we wobble it for a short time, centered on a frequency which is in the gap. If we wobble it on a frequency which is out of the gap, I'll show you something later, you get normal waves going through the solid. So we're exciting it by just wobbling it at one of these frequencies which is inside the gap. Okay. Yeah?
What happens if you wobble something in the interior with the same frequency?
Ah, that's a good question. Well, you're going to get a little bit of discomfort in the system. So you're going to get initially waves that go out when the frequency is kind of broad, and eventually you're not going to really be exciting very much in the bottom. They're going to negatively interfere with each other. Okay, that's a good question. So it's not gravity, right, which was biasing everything. So maybe it's just something that a line of, but it's all happening on the edge. So maybe, we can just focus on the edge and understand it by looking at the edge. Maybe it's just a property of a chain of gyroscopes. So let's cut out the bulk completely, right? Let's just remove it and just have our gyroscopes on the edge and excite it over here. The bulk is important. Right? Bulk is important, and the behavior is all on the edge, and it's chiral, right? Actually, this is the answer to your question. What happens if you excite it at a frequency which is, it's not sort of the answer to your question, but it's something I raised before, which is outside the gap, then you get waves going through the middle. Okay, so bulk is important. It's happening on the edge, and it's chiral. Okay. What if we kick it a little bit? What if we take our system and perturb it a little bit? So we're going to go back to the experiment. Okay, so in our experiment, this is, you're seeing a lattice of these gyroscopes, okay, arranged on a honeycomb lattice. This is a mirror. They're really all hanging over here, but you can see them down here, so we can look over here. It's an experiment, right? So it's inherently going to be a little bit noisy. In fact, it's noisy in many ways. Everything's just a little bit off center. The speeds of the motors, showed here colored by their speed, are kind of have a relatively big variance, up to 10, 20%. In fact, that noisiness is reflected in the sort of noisiness of the mode structure. It's kind of not very clean. And in fact, if we go to do our normal mode decomposition by poking it at a particular frequency and looking at the modes that develop, we find that our acoustic modes don't look anything as nice as the acoustic modes that we saw before. And the optical modes also look pretty bad. Right? But the interesting thing, as you saw before, is that if you poke it on the edge, then the edge mode seems not to mind so much about all this noise and just goes around the edge. Okay. So in fact, it keeps going around for a while. Okay. The damping is kind of much longer than a round trip time in this case over here. The mode just goes round. Here's kind of many round trips that you can see reflected in the beating. This noisiness, right, which we have in our experiments, can also be emulated in a simulation. You can really take these networks and you can really deform them quite strongly, like Vincenzo sometimes did with his bonds, okay, and the phenomenology is not particularly affected. You can even take a piece of the lattice and remove some gyroscopes and just sort of wedge something in there and excite it. And what you see is that the edge mode will come around this object and continue around. Okay? So what's going on, right? Well, you know, it's chiral, it's confined to the edge, it's very, very robust, it doesn't depend so much on the details. It's reminiscent of something that a lot of us have been hearing a lot about, which is these chiral edge modes in these sort of topological hard matter systems. So one of the things we can ask is, can we learn something by going and looking at one of those systems and carrying some ideas back to this mechanical system over here? Okay. And the natural system, whoops, okay. And the sort of natural system to look at when you poke around in the literature a little bit is a very famous model. It was one of the early models in topological kind of electronic systems. It's a Chern insulator, and it's the Haldane model. Okay? And this is a model where you have something like graphene. You have atoms connected by bonds. They're on a honeycomb lattice. They can the electrons can hop from one side to the other, like in any band theory for an electronic system. And the key ingredient that Haldane added was to have a magnetic field that is varying in space as a background to this lattice. Okay? But without worrying about the details of the system too much, let's just go and have a quick look at how much it matches onto our system. So we can ask, what is the band structure of the Haldane model, and how does that compare to our springs and gyroscopes? And what we see that, in fact, there's this sort of already a neat kind of analogy. So then we can ask, well, what if we just take the what is it in Haldane's model, what is it in this topological system that allows him to predict the chirality of these edge modes that sit around the edge? What direction do they go in? Right? Because we had no way of predicting that so far. It wasn't gravity if it wasn't anything. And the number which is used in these contexts is a topological invariant, much like the topological invariance that Vincenzo spoke about. It's known as the Chern number. Okay? And it's an integer. It's a topological invariant. You can calculate it much like we calculated, for example, the circulation of a vortex. Okay? You can calculate the circulation of this vector field over here in k-space, okay, going around the Brillouin zone. And this vector field over here, this analog of the velocity for the vortices, is given by this expression over here. It's a derivative with respect to the wave vector in k-space, in the normal mode space. So it's telling you something about the phase differences between neighboring eigenmodes in k-space. Okay? For the moment, we're not going to delve deep into this. We're just going to kind of give the definition and say that in this model over here of Haldane, if this number is +1, right, for this band versus this band, then the edge states are going to go around in a, say, plus direction. And if this number were -1, they would have gone around in the other direction. So, yeah?
I want to ask a question, but if you're going to give us a big reveal, I won't ask the question.
Okay, so let me give me a few more slides and then we'll come back to it. Okay, so great. We can take a system, and in fact, I'm not going to do this in detail, but we did this. You can take our system and you can map it exactly onto the Haldane model in the limit of having very strong pinning. Okay, so this is not just an analogy. There's a lot of depth to this. But one of the things you can ask is, well, you have this funny phenomena, and then you've sort of showed us a bunch of math, and this math can be +1 or -1. How do I see this as I'm not necessarily convinced that you're capturing what's really going on in a system. I want to see you tune something. I want to see you do something with this increased knowledge and convince me that this is the right way to think about this system before I'm going to invest all the time to understand this topological invariant. Okay? So then the question is, well, how could we do that? And so the question becomes, what is the key ingredient that goes into the Haldane system that gives it all these properties? And the key ingredient that goes into the Haldane system that gives us all these properties is a breaking of time reversal symmetry. Okay? But not the breaking of time reversal symmetry in the sort of most naive or most simple sense, which is you take your equation of motion, you take t going to minus t, and you see that you get back the same equation, like, for example, in the wave equation. Right? It's a time reversal symmetry in the quantum mechanical sense. And in the quantum mechanical sense, what you do is you take a time reversal symmetry is when you take your equations and you take t going to minus t, and you take psi going to psi star. Okay? And this is, in fact, the symmetry of the Schrodinger equation. Right? If we have I dt of psi, right, is equal to some, we have a Laplacian of psi, for example. Okay. We can take t goes to minus t, so this becomes minus I dt of psi is equal to del squared psi. So this equation is different from this equation over here. And now we can take psi goes to psi star. So we do this. And then we see that we've recovered the Schrodinger equation. We can just take the conjugate of this whole equation, and we have I dt of psi is equal to del squared psi. Okay? So in the Haldane model, in the electronic system, there's a direct link between this symmetry and the breaking of this symmetry, and the presence of edge modes. So how does that play out in our equation? Because our equation looks kind of similar, right? Well, we can try doing the same operation in our equation and see if we can identify a physical relationship between this symmetry, which is the key ingredient for the Haldane model, and our mechanical system. So, yeah?
Should we take a little break?
Let me just finish this equation, and then we'll take a break. So we can take t goes to minus t. We get a minus sign in front of here. Okay. In fact, let me do it right underneath it. So we get a minus I dt, psi 1 is equal to omega p, psi 1 plus, well, the same thing over here. And now we can take psi going to psi bar. Okay, so we're going to take k over 2 over here, psi 2 minus psi 1, I should write this out, plus e to the 2I theta, psi 2 bar minus psi 1 bar. Okay, well, if I take psi bar, I just put a bar over everything. Okay, this becomes bar, and these lose their bars. Okay, and that's the same operation that we did before, and the only thing which we had to do last time to recover our same equation and see that it was a symmetry was take the conjugate of the whole equation. So we can do that again. So this becomes a plus I. This loses its bar. This loses its bar. This loses its bar. This loses its bar. So far, so good. This is going to regain its bar. So far, so good. But there's this guy over here in the way. Okay? And this guy over here, when you take the conjugate of it, is not equal to itself. Okay? This guy over here, when you take its conjugate, can just be e to the minus 2I theta. Okay? So this symmetry only exists in our system if this term over here is real. And this term over here is real whenever theta is a multiple of 90 degrees. Not 180 degrees, but 90 degrees. So that tells us that when our bonds are at 90 degrees to each other, we have a symmetry in our system that we don't have when our bonds are not at 90 degrees to each other. And so when we come back in 3 minutes, this is going to be the degree of freedom that we're going to play with to convince ourselves that this way of looking at the system is the right way to interpret it.
least for in photonics, when you have, for example, Fouquet topological insulators
Yes.
and stuff like that, has to be a linear system.
No, this will survive. Huh?
Can I erase the board?
Yeah, just leave me this one.
Oh, okay.
Yeah.
So what happens, for example, if here the springs have some sort of inherent non-linearity?
That's a good question. We're exploring that. Weak nonlinearities don't do anything.
No, not weak. For
Yeah.
example, because I would have thought of something like a Fermi-Pascal potential or something like that.
Then you could have some worry. Yeah, that's one of the problems we're looking at. Like I don't know, really don't know the answers.
Because then your nodes are highly coupled, and you could.
Yes, you could hybridize into something else.
What I wanted to ask you about was that you sort of, when you said, let's just look at the edge. You know, I liked it as like a pedagogical thing, but you have two edges when you have just the edge.
Good question.
Having the bulk suppresses one edge.
Yes.
Which is
It
why
actually
you,
pushes one edge all the way to the other side.
Yeah.
Yeah.
It out, and that's why you get a single mode.
Yes.
I just wanted to.
Yes, you're right. I was a little bit sneaky there.
That's the way we talk about the TIs, right? Is if you have a hole in the middle of your TI, you know, you can take it.
You get the opposite amount, which we do. Yeah.
Or in the holocaust even.
Yeah.
Right?
And in fact, in this system, you just need one lattice spacing to see them nicely going
Exactly.
apart from each other.
If you have an annulus quantum Hall state, you have the other mode on the other edge.
Yeah.
Okay, I was just making sure.
Oh, you're right.
So the existence of edge modes, is that like, it sounded like that's just a consequence of not necessarily time reversal breaking, symmetry breaking.
Well, it's a consequence of having a gap in the first place.
Yeah.
And then the question is, why did that gap open? And you can open a gap for many reasons. And if you open it for the quote-unquote wrong reasons, you don't get the edge modes like that. You'll still have Rayleigh waves in a very big system, but you don't get edge modes like that.
But you could have time reversal symmetry and also
And the gap.
and edge modes.
Not chiral ones.
Right. Yeah, so chirality is the criterion for.
Yeah.
Sorry?
Yeah.
So you mentioned that you have a doubling of eigenstates, the left moving states.
Well, it's because the right moving pick up a negative frequency, so they like the left moving.
Yeah.
So it's a little artificial. It's just that's how it works out.
Okay, no, but genetically, they like if I look at the Brillouin zone of your lattice, then where would these live? Where would these, where would the doubling, where would the double states live?
Oh, you get a copy of the two bands underneath. So it's 4 bands,
Okay.
2 positive frequency, 2 negative frequency. But there's zero information. Like you just take omega to minus omega and everything
And
else
it's
is the same.
thing.
Yeah.
Okay.
So there's a degeneracy because you're dealing with right and left. Stuff like that.
So you're saying it's because the time reversal symmetry is broken?
Yes.
So that's why there's a gap. Just the same as
Yes.
graphene?
Yes. Exactly. But what we're going to do now is we're going to break it the other way and make them go the other way.
And then so what determines the direction?
Aha.
So
Well,
the
that's
way you put
the Chern number.
The Chern number.
Yeah. So I'm going to show that now. That's this horrible number I put up on the board earlier. That's this horrible number I put up on the board earlier.
Not horrible.
No, it's not horrible at all.
So, I'm not really familiar with all of these steps. What is the physical implementation of Chern?
That's a good question. I can give you all sorts of mathematical interpretations of the Chern number.
Like a topological charge.
It's sort of like a topology. Let me try this. Right? We can try different things. I don't have one that I really like, so I'm probably going to disappoint you. And turns out a lot of people I speak to don't really have one that I really like. So, you have your eigenmodes in k-space, right? Now these eigenmodes can have a phase to them, right? And usually you think that this phase is kind of, in principle it's arbitrary, right? Because the phase of any one eigenmode when it's on its own is arbitrary, right? But there could be a connection between the phases of eigenmodes in k-space.
Okay, so you're saying that the eigenmodes itself are coupled
Yes,
to the phase.
through a phase, through a Berry phase.
Okay,
And so if you have such a coupling, well then you need to consider gradients of this phase.
I see.
And the gradient of this phase is the velocity field that I wrote down. And then you can have charges, you can have non-trivial topology to this phase field. In other words, you can do the following exercise. I got a bunch of eigenmodes. I'm going to start connecting their phases, and I'm going to make them as equal as I can. And you're going to go, 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 you're going to go. When you come back, you've got to be able to come back to your original one, but you might have picked up 2 pi. And that's the Chern number.
The reason why you pick up the very phase is because you have the bonds having multiple.
So Chern number
Yes.
is like a winding number?
Yes. It's a winding number in K-space.
Okay. So it's basically Chern
It's like a magnetic field in K-space. And it's the flux of the magnetic field in
So
K-space.
Chern number is basically telling you about like how coupled these different normal modes are.
In some sense.
Okay.
But
Not exactly.
yeah, exactly. Okay, let's get started again. So so we ended by identifying, right, by analogy with the Haldane system, the key ingredient that in that system determines the fact that you get these chiral edge modes, and that's this breaking of this reversal symmetry. And we looked at our equation of motion for a mechanical system, and we related whether or not this symmetry is broken to a geometric thing, to whether or not our angles between our gyroscopes are at 90 degrees to each other or are not at 90 degrees to each other. Okay? So let's see, how long do we have? 20 minutes? Yeah, I'll go through this. Okay, so that tells us something interesting. It's a little bit funny. So let's look at the simplest case in which we can just convince ourselves that this is true. So we're going to take a chain of 3 gyroscopes. We're going to take this chain of 3 gyroscopes, and we're going to have their bonds, the centers of their orbits, all connected in a line. So that all our thetas are the same angle. They're all 0. Okay? That makes this real. So we can evolve our system. We can evolve it by some time. We can then perform the time reversal symmetry operation, and then we can go a little bit further, okay, in time, and then we can reflect back. And what we find is that we get the same state that we had when we had at the beginning. But if we take a system of gyroscopes where the bonds now have an angle to them which is not 90 degrees, and we do the same thing, we go forward in time, we reflect, we go forward in time by the same amount, and then we reflect back, then our final state is not the same as our initial state. So the angle kind of breaks the symmetry. This is kind of a little bit funny. How can I think about this physically? Well, in the case of springs, there's a simple way to think about this. What's kind of, if it's a symmetry, there should be some sort of energetic basis for it, right? So let's think about that. Well, let's consider 2 gyroscopes, right, which are connected by a bond. And let's say that our 2 gyroscopes are deflected in this way over here, which is perpendicular to this bond over here. Okay? So I'm going to displace this one down and this one up. So what does the conjugation operation do to these gyroscopes? They're connected by this spring. Well, it takes this one to here. It's just a reflection locally. And it takes this one to here. Well, what is the length of the bond? Right? It hasn't changed at all. Okay. Good. What about the perpendicular case? So if this is now my bond, and I've displaced this gyroscope this way, and I've displaced this gyroscope this way, and now I do my symmetry operation. I reflect this one here. Well, now it goes to here, and this one goes to here. So what used to be a spring length, which was this long, has now become a spring length which is this long, right? So it's not the same length, but it's a spring. And what's changed is that what used to be some amount of stretching has now become the same amount of compression. So the energy of the spring hasn't changed. Right? We've just changed the signs of delta L, and the energy goes with delta L squared. So if your displacements can always be made such that they're either co-aligned or perpendicular to the bond joining the 2, right, then you have a physical symmetry under this reflection over here. Okay? And that is the counterpart of this statement that when the angles between the bonds are always at 90 degrees, then we have this time reversal symmetry. Yes, Vincenzo? Yes.
That means state is 0 energy, but you're saying here you generalize the state within the night, same energy kind of.
Yes. Yes. So in your case, the bonds can't move, so you have this one, right? But this one would be you can't do because you can't stretch them.
But just if this equals 0, you say
Yes, exactly.
That manifold. It's just that you do it only with a linear order.
Exactly. Exactly.
But the first case, I don't understand. So the first case is the case where it is time reversal broken. Is that?
No, in both these cases, the energy hasn't changed, and that's because there was an alignment of the bonds with the axis about which we're doing the reflection.
Alignment of the bond. So the two dots that's the original orientation of the.
Original psi star, and in this case, it's original psi star.
So what did you mean by alignment of the bonds? I mean, I understand the second case. That's a special symmetric situation. But in the first case,
Well, if I had,
I thought you were demonstrating a case of where theta equals to 0 pi,
yes,
or it's not, and it's not. You know, I thought you were going to contrast two examples. One has special value of theta, doesn't break time reversal, and the other does.
well, what I'm saying is that what emerges when we calculate the values of theta that don't break time reversal symmetry
Okay.
is that it comes out to be 0 or 90. And that's a little bit funny because the 0 case is easy to understand, but the 91 is not. And so this is the origin of the fact that you recover the symmetry.
I guess I'm misunderstanding. Where's theta on there? And then that's a first picture.
0, 90.
I see. It's
Yes, it's the angle of the bond.
the angle of the.
Yeah. But I mean, you know, if you don't like this way to think about it, you can just see it directly from your equation.
Also, I didn't quite understand your analogy with Haldane model. I mean, in Haldane model, there's a very special thing where there's no magnetic field going.
Yeah.
on there. There's no average magnetic field.
Yes. So what's our magnetic
Here,
field?
there's an analog of the fact that you have gyroscopes. Each one is an effect in the magnetic field of gravitational magnetic field.
No, I can switch gravity off.
Well, then now
Everything works the same. It's not an important part of the story of how the
Okay,
edge
so in
motor
Haldane's
emerges.
model,
Yes.
it's an important
It's yes,
ingredient because with a finite magnetic field,
yes.
you're kind of having a.
You have this
Well,
Hofstadter
with the
problem.
average
Yeah,
magnetic
yeah,
field.
exactly.
But the novelty of it, even if the average magnetic field is 0, you're still getting Chern number.
Yes, and we're getting, but the way that manifests, I'll come back to this at the end, right? Is that you can get non-trivial phases for second nearest neighbor hopping, right? And in our case, they're coming from this relative orientations of the bonds and this first order derivative. Okay, but you know, this is a lot of kind of like analogies with stuff that many of us aren't familiar with. At least I wasn't familiar with when we started with this. What can we do to see whether or not this is really determining this edge mode that we wanted to understand about? Well, you know, if it's all about the angle of the bonds, and then the angle of the bonds when it's 90 degrees, we have a symmetry, all these effects should go away. Let's see if we can take our lattice and distort it and make all these effects go away. So what we did is to take our honeycomb lattice, distort it, and you can see that you can easily distort it into several configurations, many that are sort of like this, but one of them in the middle that has no angle in there. Let's see. And so then we can go and look at our band structure in these two cases. And indeed, we see that whilst in this case we had this gap, when these bonds come to be all 90 degrees, the gap goes away and we get these bands touching at particular points. So now we can go back and we can poke it. We can take our bricklayer lattice and we can poke the edge. And we don't really have a gap, but we can poke like close to where we think the gap is, and no effect. In fact, we can go one step further. We can only not just stop over here. We can go all the way to the opposite lattice. And so we can take this lattice, we can take the bricklayer lattice, which is time reversal symmetric, and this one, which is not, but geometrically it looks like it's not in just the opposite way of this one. And in fact, when you excite it, in this case you get a clockwise mode, and in this case you get an anti-clockwise mode. So this geometry of the angle, which kind of is intimately related to this breaking of the symmetry, is determining the direction of the mode. And in fact, you can go back and you can calculate the Chern number, okay, for this structure over here, and we find +1 and -1, and we had speculated that this was why it went right. In this case over here, the bands are touching, so we have no Chern number. In this case, when the gap is reopened, we have a different sign. Here we have +1, here we have -1, and that is determining now the direction of this other mode over here. Okay. In fact, you can have static structures, but you could even consider doing something which is very hard to do in other systems, which is mechanically distorting your lattice whilst it's poked, and you can have a strain-induced transition from one Chern number to the other. You can have a topological phase transition, which is what this is, the two bands touch, induced by a simple distortion of the lattice. So we started with a mode that went around one way. We came through our symmetric configuration, and at the end, we can see that the mode is going around the other way. Yes?
If you go through that symmetric point in this transition, you would expect to radiate a good amount of energy out of it.
Yes. Yes. So in fact, if you look at it, let's look at this gradually. As we approach, we're closing a gap, right? And we're losing the localization of the mode at the edge. As we lose that, we see the mode going into the bulk. As we come through back the other side, we have still some energy in the bulk, but the energy which was on the outside stays on the outside and now starts going around the other way.
What happens when there is no edge mode? Like, where is the energy going?
When there is no edge mode, it goes into the bulk.
It goes into the bulk.
Yeah, it's just like a crystal.
Okay.
If you poke the crystal, the waves go into the bulk. Right?
So if it's a square lattice, we don't have.
That's a good question. So what other lattices do this? Right?
You need to have two atoms in your unit cell, at least.
Yes, you need to have two atoms in your unit cell. You could do this in a square lattice by making every other site a different strength. Right? In fact, that's a way to open a gap in any lattice. So we could have taken this lattice and we could have taken, let's say, this lattice. This is our unit cell. We could have made this one pinned with twice the strength of this one, for example. Or we could have changed the spring constants in the bonds. Yes. Yes, but you can ask another question, which is it sufficient to have an optical and acoustic band in this structure with the gyroscopes? Not so sure, exactly. So let's do that. Right? So let me just skip this slide for a second. Let's take the same system. Okay, it's the same system. It's gyroscopes. We've broken the time reversal symmetry. But what we're going to do now is we're going to take the pinning strength of this side and make it very different from the pinning strength of this side. Okay? So we have now two different atoms in the unit cell structure. Okay? They're still gyroscopes, still same equation motions, but we have this, if you like, other way of opening a gap, which is breaking kind of different symmetry. And if you poke it in the gap frequency, we see that we lose the effect. Now this system, I don't have it here to show you, but has a gap, just like the other system. It has the breaking of time reversal symmetry, but it also breaks this other symmetry, which is this inversion symmetry over here, the two sides. And if you do that enough, then you lose all the character. Right? Yes. Sid. Huh? If the two atoms are different, you open a gap in graphene too here. I think, yeah. That's balls and springs. That's Vincenzo. If you do this in graphene, does it open a gap? Okay. Really? If you change the strength of the pinning at the two sides, then you... No, it doesn't have an edge mode, but it opens a gap, doesn't it? That opens a gap, yeah. If you break AB symmetry, you open a gap. Sid, do you have a question?
I was just saying your design changed at the same point as the possible.
We're intrigued just as much. We don't know, but that's one thing which we're wondering about. So what I showed you in that case over here, this is just kind of a comment in passing before I show you two other lattices, just to kind of whet the appetite for your question a little bit. What we did was to take this side and make it different from this side by changing the pinning strength. So that's, if you like, one axis, which is the difference between these two. And the other axis is this angle axis. Right? And so what you see is that if the two sides have the same strength, which is sitting at the same strength over here, ratio of 1 in this axis over here, we can go through a topological phase transition. Red, what's plotted in red is the value of the Chern number. Okay? And in this case, it's -1. So here it's -1 and here it's +1. So we can go towards the honeycomb from the bricklayer lattice, and we can pick up a non-trivial Chern number. We can go from the brick lattice to the butterfly lattice the other way, and we pick up a negative Chern number. But at any point in here, we could also go this way. We could break this symmetry over here between the two sites, and we can open a gap, but we have 0 Chern number. We have no topology in a system, and we lose the edge modes. And in fact, we can go from here, where we're deep inside one of these topological phases. We can go up, and we can lose that Chern number by breaking the symmetry. Okay, so I'm pretty much at the end of what I want to say, except I want to show you, one question which Sid asked was, does this depend on, for example, the Poisson ratio? Like, I've shown you a honeycomb lattice, I've shown you bricklayer and butterfly, which were deformations of each other. But you can ask, what in the lattice structure, other than the time reversal symmetry breaking, is the important ingredient? What lattices will do this? What lattices won't do this? What if I have 3 bands instead of having 2 bands? All these sort of questions. So that's current research. We're exploring these questions at the moment. But I just want to show you a couple of videos. This relates also to Vincenzo's and Tom's talks. At least I guess, yes, Vincenzo's and Tom's talks. I'm showing you over here a Kagome lattice. In this case, it's a twisted Kagome lattice. Okay? And same system. We're going to poke the edge. And we can see that, in fact, just as in the honeycomb lattice, we're able to get a wave packet that goes around in one direction. This other system over here is Kagome again, but this one is untwisted. And we have the same story. So there's at least 2 other examples in which we can get this to work. In this case, the Kagome lattice was untwisted. In this case, it was twisted.
Like nodes in
Yes. Yes. So it's harder. Yes. Behind the wave packet isn't as localized as the other one. That could be dispersion, right? It could also be something a little bit different in this system to do with the other 2 bands. Yeah.
So in Kagome lattice, is that spectral configuration that node state? That's honeycomb.
We're playing. Ask us in a month, and we might have an answer.
It seems that you cannot find a configuration that follow the angle either 0 or 90. Is it doable?
You mean, can you have a topological phase transition in the Kagome system?
Yeah.
That's a good question. We're trying right now. We don't. Yeah. This is really like, up to date, current, where we are. Yes.
What if you twist the Kagome lattice more? Does the wave
I don't know. That's what we're playing with at the moment. I mean, you're saying with a Kagome twist lattice, you could find a way of addressing the question that Sid was asking, for example, of playing with the Poisson ratio or other thing. Absolutely. Where that's one of the directions which we're going in at the moment.
In the honeycomb lattice, you say topological phase transition. Is it the real phase transition? If you can choose theta and the other parameter is the speed of the
Well,
The speed of
it's a topological phase transition in the sense that I understand the topological phase transition. You deform some parameter in your system. Your bands come together, they touch, and then as you continue going through this parameter, they open again, and the churn number has changed. So it's for a churn insulator.
so the churn number jump from 1 to -1.
Yes.
What's the order parameter? Is that in a continuous changing order parameter, like the speed of the edge space?
The direction of the edge state is
The
dictated
speed
by
of-
the churn
but
number.
When theta is exactly 90, it's 0, right?
Yes.
Okay. So it must change continuously. So that can be the order parameter.
There's no local.
Yeah, exactly. Like,
That's why it's called topological.
I'm not sure. I'm not. So at the risk of
So
saying
is
something
there
wrong,
a
I don't think you think about a topological phase transition in the same way as a normal phase
Yeah,
transition
yeah.
where you have an order parameter that changes. It's a little bit more subtle.
So
and-
is that diverging length scale at the critical point, just like normal phase?
That's a good question. So I don't know in general, but in this system over here, as you approach this transition, the localization of the modes decreases. But that's also because the gap is kind of
The gap is
narrowing. Yeah.
low frequency, long wave.
Yeah. Exactly. So I think that puts us roughly out of time. Let me conclude by just playing this video again and thanking everybody who really made this happen. Lisa, who kind of really built and calculated and really mastered the system over here. Ari Turner, who was really pivotal in starting this whole project and guided us through, very patiently guided us through our modest, building up our modest understanding of topology in other systems like electronic systems and relating it to this. Dustin Kleckner, Liz Mary Reed, and Vincenzo. Thank you.